Hello there. I'd like to talk to you about caching and the hierarchy of memory. For starters, what is caching? Simply put, sometimes we have memory units or storage units that are very, very big because they're cheap, but that also makes them very, very slow. And sometimes we have storage units that are very, very fast and thus expensive and thus very, very, very small. For example, if we had like let's say a CPU, and we were just talking about the memory that the CPU itself could hold, in its CPU registers. We have a very small number of registers inside of the CPU compared to system RAM or disks or whatever. So we can't actually hold that much memory, but at the same time, the CPU registers are lightning fast, even compared to system memory. So that kind of sucks, right? Because the system memory is way slower than the CPU registers. Why can't we just have more registers? Well, it's too expensive. So caching is something that you can kind of use to get the best of both worlds. You can have something that's very, very fast be your primary place that you try to store things and look for things to get them and set them. And then when it runs out of space, you can just kind of push things to something that's a little bit slower, but larger and cheaper. And then hopefully there's a pattern of access that actually makes sense. Hopefully you're not accessing your data and instructions in a totally random way. So that when you access in a pattern, then algorithms inside the machine and the operating system can kind of figure out which items are best to take out of the small storage device. And that way we can sort of keep the most frequently or the most often or the most recently used things inside of the fastest device. This is kind of a way to get the best of both worlds, kind of a way to leverage the best of both worlds. Okay, so what am I kind of talking about? Let's just suppose for the sake of argument, let me draw this a little bit. Suppose for the sake of argument, you have something that's really, really slow, but it's huge. A huge storage thing. Maybe this is your disk. Maybe this is your system RAM. I don't know. There's many levels to this. Then maybe you have something else that's a little bit faster and thus a little bit more expensive, but it's slower. And then maybe you have something else that is like really, really fast, but it's super expensive, so we can only make a really, really small version of it, right? So imagine that, you are I don't know, we'll say the user. The user of these things is actually usually just like the CPU or something. But let's say that you're the user and you want to look and see if some piece of data you want is stored in there. Maybe you have memory location 45 or something, or 44. That you want to check for. You're like, what is the data at memory location 44? I'm totally making this up. That we wouldn't look at memory location 44, but suppose you are. So if memory location 44 or this item, whatever that you're looking for, is in the super small and fast thing, then awesome, you don't need to look any further. But if it's not, we'll call that a cache miss. We'll say, well, it's not in there. Oops, it's not in there. So we call that a miss for a cache. And that means we just have to check the next thing. We'll say, all right, well, if it's not in there, is it in the next fastest thing, the thing that's like a little bit slower and a little bit bigger? If it's in there, we call that a hit. We would call it a hit if we found it on the first try also. But if it's in there, we call it a hit. And if it's not in there, we call it another miss. So we'll say miss. And then finally, we'll check maybe the biggest thing that we have available, and we'll go, all right, is it in the giant thing? And usually it is going to be in the giant thing because if we're talking about program instructions or program data or something like that, the data is at least going to be on your disk drive in almost every case, right? So, or your hard drive. So you could imagine maybe this green thing is the CPU registers or the CPU cache or something very, very, very fast. And you can imagine this blue thing here is perhaps system RAM. It's like a little bit bigger, a little bit faster. And then the red thing is your hard disk, which does definitely have all the data, but it's really, really, really slow. And we're hoping not to try to touch the red thing because it's going to cost us a lot more time. And then same thing for the blue. So the first time we look for this piece of data, we missed twice because it was only in the red thing, the disk, that we'll call it. But then suppose we come along later and we look for that piece of data again. Maybe we're inside of a loop. Maybe our function gets called multiple times, and for whatever reason, we check. But when we originally found the data in the red box, by the way, it was sent up through the cache and sort of copied into all the other devices. So, when we couldn't find our data anywhere in the green or blue, it was copied from the red to the blue and then to the green also. So it's actually everywhere. And then the next time we try to look for that same piece of data, we'll have a hit because it's just sitting in the CPU. Or sorry, not the CPU, but just the fastest thing, which you could imagine as being the CPU or the CPU cache or something, right? So notice how once we have a hit, there's not really any need to go look onto the slower devices. So again, if your access patterns are not totally random, then you can have most of your important data sitting in the fastest device based on how often you need that data or how recently you've used that data or whatever. So great, we have a lot of hits. We're now getting lightning speed because we're just like reading only from that green area. Suppose some time passes and you start filling up the green thing, the fastest thing, with lots of other data, and it overflows because it is a small place for data. So eventually we'll have to start purging some of the data that we're not using anymore, and maybe it's this OX44. Man, that X is awful. I'm still getting used to this pen. Let me just try one more time. Oh, when I lift up the pen, it kind of drags a bit. So we've kind of filled up the green area, and there's not enough room for all the data that we want. The system realizes that OX44 hasn't been used in a while. It doesn't seem to be a part of the current working window data set, and so we'll just purge it. So the system just says, all right, let's just erase that from the green. But even when it erases it from the green, the fastest storage device, it might not erase it from the blue. Because the blue is bigger, it can hold more data before we start having to erase things, right? So that means there's a pretty good chance it's sitting in the blue. So if we try to access it again, I'll just put a red X here to indicate that we have a miss. So we miss the fastest device. That sucks. Then we check the next fastest device, and it's in there. So we're going to call that a hit. So, you know, we didn't get to use the fastest device, but at the same time, we also didn't have to use the slowest device. So this is still kind of a win, right? Suppose, oh, and then by the way, once we find that hit, once we actually hit it from the blue device, then the data gets carried back to the green device, the fastest device, because the system now considers OX44, that address or that value, whatever, to be part of the working set of data that we're currently using. So the moment we hit something, it gets brought up to the fastest device in the hopes that maybe we'll try to request it again in the near future and save a bunch of processing time. So suppose for the sake of argument, then a bunch more time passes and it has to be purged again from the fastest device. So, you know, we're accessing lots of data. We're filling up that green thing again. Eventually there's not enough room. We have to purge some old stuff. So we purge the 44 there. And then even more time passes and we have to also purge it from the medium speed device, the blue square, because that also can fill up at some point. So that sucks. We'll never purge from the giant storage device, which is like your disk drive usually, or your hard drive. So it'll still be there, which means eventually when we try to request 44 again, we'll go through the original process. We'll just say, you know, going through. Well, I'll just write the word miss. We'll just go miss here, and then we look here, and it's another miss, and then we look here, and it's a hit. I'll put hit. So in that case, when a lot of time passed and all the other caches kind of filled up, then we didn't really get any benefit, any performance boost from using caches. In fact, we took a little bit of a penalty on those two misses because we got to check one thing, whoops, and then check another thing, whoops, and then finally we hit the red thing, which is giant and has the data we wanted. We could have just gone there in the first place and saved a couple of, some CPU cycles because we wouldn't have had to do the two misses. But checking and missing is part of the process of using a cache, and so it's worth it because most of the time we'll hopefully be hitting a lot of cache in the green area and even more cache in the blue area. So that's the basic idea of caching kind of within a system. Let's see, what else did I want to show you here? We got slow, medium, and large, and maybe just another example that you might relate to more. Suppose you go to an internet website, and on the website there's lots of images and things like that. Well, those images are usually cached on your local machine inside of your browser's cache area. What am I even talking about? First time you go to a website ever, the images get loaded from the internet. Imagine the internet as being something that is like very, very, very big, because it's like at this point I think since 2020 it was over 64 zettabytes, and a zettabyte is a trillion gigabytes. So 64 trillion gigabytes of data on the internet, so huge, right? But the internet is kind of slow. Even if you have a lightning fast connection, it's probably still slower than accessing your local hard drive. Definitely way slower than accessing your local memory. Although most people, when I recorded this video, have internet connections that are significantly slower than their disk drive or their SSD. Anyway, so the internet is huge, but it's slow. And I guess it's cheap compared to the amount of storage and the speed you get. So you download the image from the website from the internet, and that's like takes a lot of time. If you do that every single time and there's lots of images, you might feel like your internet experience is slow. You might see images kind of like loading. You know, even in the modern era, if they take just like a moment to load, then you kind of think like, whoa, there's like a lot of delay here, right? So, but then the first time, we would call that, I guess, a miss on your local cache, and then we would hit on the internet. So the first time you load it, it actually your browser will actually save a copy of that data to your local disk area. And well, the next time you go to that website, instead of looking directly to the internet to get the images, your browser will look to see if you have a copy saved already locally on your disk drive or your hard drive. And if that's true, then your computer will just load the images from the local machine and not from the internet, and then your pages will seem like they load a lot faster. So that's kind of the concept of caching in a slightly different way. You know, the fast, expensive thing is your hard drive. The slow, cheap thing is the internet. You can imagine there are many levels. I mean, this diagram that I drew, there's 3 levels. In your CPU, you have CPU registers, the fastest thing, and then you have L1 cache, which are almost as fast as the registers, and you have like some amount of kilobytes that you can store. And then your CPU also has L2 cache, usually, and then depending on what kind of CPU you have, you might have L3 cache. So that's 4 levels right there. And then beyond that, you know, there's system RAM that can cache some data for your CPU. It's a lot slower than the CPU caches, but, you know, it's larger. And, you know, eventually we can just get basically down to your hard drive in the slowest case. So let's see, what else can I tell you real fast? Oh, I wanted to show you a diagram. Let's see. So let me show you this diagram right here. I found a diagram of this on Wikipedia. It's called Computer Memory Hierarchy. And so this is what I talked about in the beginning of the video. We want to talk about like the hierarchy of memory. The hierarchy is kind of like a pyramid. The reason it's a pyramid is so that we can kind of remember that stuff on the top is very small. Notice how the thing on the top, it has less area to work with, and the things at the bottom have a lot more area to work with. So the thing that's written in the middle here, actually, let me go to the actual image of it, because I think I like it the way it looks a little bit better. Oh no, I wanted to do this because I already had it. Okay. So the things at the top have a very small size and a very small capacity. And you can imagine some examples are processor registers, like our CPU registers, but they're very fast and they're very expensive. And there's this little term written down here, or this little description saying power on immediate term. That just basically means this is volatile memory. And so, you know, the moment you the moment you disconnect power, shut down your computer, you just lose that. It's just gone forever. Then kind of, you know, getting a little bit bigger and also a little bit cheaper, but also a little bit slower. We have the small size, small capacity category. You could imagine this is your processor cache, which is just, you know, a cache on your processor is just a little data storage area. You know, like I said before, that sort of backs up the CPU registers. It's where the registers first look for their cache. Still very fast and very expensive, only a little bit, you know, cheaper and thus slower than the CPU registers. Then we have like medium size and small size and large size and, you know, whatever. Different sizes and categories. So kind of going from the fastest to the slowest here. You know, once we hit cache, then we can consider this to be, you know, still pretty fast, way faster than the disk, but random access memory or system RAM is just a lot slower than the CPU, but it's, you know, faster than the disk. And then you can imagine other things that are a little bit slower, but a little bit larger, could be flash memory, USB memory, and so forth. And then pretty slow here. The slowest that I ever deal with personally are hard drives. Even your SSD being way faster than your old disk drives is still considered very slow compared to system RAM. But they're huge, right? And then kind of like at the very bottom of this pyramid is tape backup, incredibly slow, but incredibly large for the money. And that's why this is sometimes used still. And that, my friends, is the hierarchy of memory. I hope you learned a little bit of stuff and you had a little bit of fun. I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.